Okay, conservation of momentum. So we just finished going over impulse, which is a fancy name for change of momentum. There's two ways to calculate impulse. So now we're to the main, at least what I consider to be the main application of momentum, which is conservation of momentum. Now the word conservation, we did a lab on this already, so this is kind of review at this point. The word conservation has a very specific meaning in science. Conservation means what you start with equals what you end with. Now, where do we apply conservation of momentum? We apply it to two things. We apply it to collisions, which is easy. That's what we have right here. This diagram right here. See, here's what's going on. This guy's not paying attention in this car because he's texting his friend, and he looks up and, oh dang, who's in front of him? The Big Joe's beer truck. Okay, so bam, collision. What's going to be true in that collision? The momentum before the collision is going to equal the momentum after the collision. Okay, when else can you use conservation of momentum? In explosions. Now, it's not the type of explosion you think of like you see in a movie, a car exploding or like a building exploding. In physics, what we mean by an explosion would be something like this. It's two objects coming apart. So here we have, what are the two objects in this situation? The cannon and the cannonball, right? How much momentum do we have before the cannonball gets fired? 0. So how much momentum will there be after the cannonball gets fired? 0. If the starting momentum is 0, the ending momentum is 0. Well, how is that possible if the cannonball's moving, right? If the cannonball's moving, doesn't it have momentum? Yeah, but you got to remember, this way is what? Positive. That way is negative. So the thing that has to be true, since the starting momentum was 0, that means that this positive momentum of the cannonball after the cannonball is fired equals the negative momentum of the cannon. Okay? Now look, full disclosure here. Full disclosure. If you walk out in the intersection right out here, Silver Spur and Hawthorne, and you see two cars collide, you'll probably think, oh, Spalding just talked about conservation of momentum. That's awesome. Momentum was conserved. But you'd be wrong, because look, this is really only true. Hey, this is really only true if no outside forces are present, such as friction or, let's say it's two cars colliding. One driver has their foot on the brake, the other driver has their foot on the gas pedal, so the wheels are like still digging into the ground. If there's any other force other than the force of the collision itself, then you can't do what I'm showing you, right? But don't worry, every problem in the homework set, all the problems in the homework set will have no outside forces. All right, so let's look at this equation. And what we're saying is initial momentum equals final momentum. But look, if you have a collision or an explosion, how many objects must there be? 2. So what we're saying is momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. You take your total starting momentum and it will equal your total ending momentum. Okay, so what would momentum 1 initial be? M1 V1 initial. What's momentum 2 initial? M2 V2 initial. Momentum 1 final? M1 V1 final. Okay, you guys getting this? Okay, so let's look at it. Let's look at a problem, and then what I want to do is show you guys a video. Okay, so here's a problem. So copy this down into your notes. I'll give you 5. It's a very easy problem. It's not difficult at all. I'll give you 5 minutes. Try it out. All right. Shh. So here, it's conservation momentum. You know what? Since we only have about 5 minutes left, we only have about 5 minutes left, so I'm just going to solve the first one here. And then tomorrow I'll pick up with talking about kinetic energy loss. Whenever you have a collision, or you know what, I shouldn't say whenever, because there is a collision type where you don't lose kinetic energy. But I will say this, in most collisions, kinetic energy is lost. And if you think about it, it'll be true. Think about two objects colliding. Before the collision, you have kinetic energy, right? In most collisions, you lose almost all the kinetic energy. Even though momentum's conserved, you lose kinetic energy. All right, so how do you solve number one? The velocity of the truck after this collision. So let's just label everything. So the car is going to be M1. That's 1,200 kilograms. The truck will be M2. That's 9,000 kilograms. So this 25 is going to be V1 initial. This 20 is going to be V2 initial. And then what's the 18? V1 final. If you look at our conservation of momentum equation, the only thing missing is V2 final, which is this right here. V2 final is the velocity of the truck after the collision. So guys, if you didn't get this right, the answer comes out as 20.9. The velocity of the truck after the collision is 20.9. If you didn't get it right, I mean, it's simply just, all it is algebra. So look, you probably would like to do it this way at the best. So M1, V1 initial, that comes out when you multiply them out, that's going to be 1,200 times 25. This is 30,000. 30,000. This right here is going to be 9,000. What's that? That's going to be 180,000. This right here is going to be 18 times 1,200, 21,600. And then M2 is 9,000, right? So look, when you solve this for V2 final, you're going to have 210,000, which is these guys added together, minus 21,600 all over 9,000. So that's going to be 210. Did I do that right? Minus 21 divided by 9,000. Yep, 20.9. All right.